Okay, so today we're going to learn a little bit about modern physics. Modern physics is the branch of physics that began in the 1900s and is continuing on today. So we're consistently learning more and more about modern physics as the days go on. And even new experiments and new findings are coming out by the hour. So modern physics is consistently developing today. Everything prior to the 1900s, so kinematics, forces, energy, waves, all of that stuff was regular physics. Now we're into modern physics, the new physics, the stuff of today. So Schrodinger's cat. Schrodinger thought of a Kerdunken experiment, or a thought experiment. And what he decided to do was he decided to take a cat, put it in a box, and set it up to some timer, whether that timer be based on atoms, radioactive decay, or whatever. This is just a thought experiment. So he takes a random timer. It can go off whenever, whether it be in a few seconds or a few years, or maybe it never goes off. So what he hooked that timer up to was a vial of poison. Now, this is just a thought experiment. Didn't actually happen, so don't worry. So you have a cat in a box hooked up to a timer, and that timer's hooked up to a poison. So he closed up the box. Is the cat alive or dead? He asked himself. Well, what we learned a little bit with waves with superposition was he came up with the conclusion that we have superposition of two different answers. So at one point, the cat is alive, and the cat's in a live state. And at the other point, the cat is in a dead state. And while the box is closed, we believe that both are true. So it's in a superposition of those 2 points. So my question is, how do we know whether or not the cat is alive or dead? The only way that we can check, the only way that we can know with certainty is by making the measurement. And therefore, we learn a little bit more about the principle of superposition. We learn about the superposition of 2 different states, the state of being alive and being dead. And we learn that maybe it's 50-50. Now, this is going on into a little bit more of quantum physics, but we learn to recognize that electrons and elementary particles appear in this type of quantum state where it's all based on percentages. It's either 50% here or 50% there. You don't know until you take the measurement. Okay? Now, what I suggest is if you don't already have the notes open, open them up and go along the slides and this video at the same time. And if any of the things that I'm going over is unclear, ask me in class or go on YouTube or some other video site and take a look at some of these concepts. And there's a lot of amazing videos out there that can really describe these things well. All right. So a long time ago, we learned a little bit about old physics. We learned a little bit about atoms and how they're indivisible particles. We learned a little bit about Newton's laws of motion. And in the last chapter, we learned that light's a wave. Okay? And it can be proven by 2 different ways. We remember diffraction is how the light spreads apart. So over here, I have a quick example of diffraction. We have light ray fronts coming towards a barrier. And as they approach that barrier, we use Huygens' principle to recognize that in the very center, these are little particles, or little point sources of waves. And we know that with point sources, just like if we took a rock and we threw it into water, it would produce a wave front that expands out radially from the source. And that's what we're seeing here. That's why if you stand behind a wall, you can still hear the music from a speaker without actually having to see the speaker. And polarization, we remember if all different light waves are coming in all different directions, the polarizer says, if we have a vertical polarizer, only vertical light's allowed through. If we have a horizontal polarizer, only horizontal light is allowed through. And if we take a vertical and a horizontal polarizer and we put them on top of each other, we get little or no output. And both of those prove that light is a wave, or at least prove that light has wave-like properties. But in the 1900s, we started to see a little bit more. And we started to question a little bit more about the facts that we knew. We performed what's called a black body radiation experiment. What a black body object is, it's an object that can absorb all of the light traveling at it. It doesn't emit any light. No light reflects off it. It's a perfect absorbent. Okay, so it attracts light, and it absorbs lights of all different wavelengths, anywhere from radio waves to gamma rays, visible light, everything it'll absorb. And what was postulated was that the higher the frequency, the more that the black body would heat up, the more energy that would be put into that black body. And that black body is going to emit a certain spectrum. So we know that if we were able to see infrared light, if we use infrared goggles, we see that our cells emit infrared light. That's because our molecules in our body are vibrating at a specific frequency that emits infrared light. And we see that through red, if we were looking through an infrared camera. And we were expecting that the higher energy that we put into, the higher we would see of radiation, the more radiation that we would see coming off that black body. But we didn't notice that. So how do we explain that the higher the frequency is not the higher the energy? How do we explain that relationship? Because that's what the wave-like properties would imagine. Well, now we start to dive into quantum physics. When we can't think about what the answer is, we develop our own physics. That's what we did with calculus. We couldn't figure out math that would make it work, so we developed calculus. Now we're going to develop quantum physics. So a brilliant man by the name of Max Planck proposed the idea of a quantum to explain black body radiation. So what a quantum is, it's a small little bundle. It's a little bit of energy. It's indivisible. It's just a small little section of it. So it's like if I take a baseball, and I can't take that baseball and I can't break it up. I just take that baseball, and that's my small amount of energy. I could take 100 baseballs and throw them out at you, but I can't have 99 and a half baseballs. I can't break that up. That's my specific amount of energy. And what we noticed was, we noticed that the energy emitted was only a specific quantized number. So imagine if it was just whole numbers. We got either 10, we got 20, we got 25, we got 26, but we never noticed anything between those whole numbers, those specific quanta. And when we broke it down even more, we learned a little bit more about Max Planck's number. We learned that that smallest number that we could see, in my case I said it was a whole number, but in his case it was 6.63 times 10 to the negative 34 joules times seconds. So we'll explain this a little bit more, but it's important to note that this is on the very, very front cover of your reference table. So if you have your reference table, I'd suggest taking it out, take a look at it, because we're going to need to know this number when we go further and further into modern.